Welcome to an example of an application of first-order differential equations involving a falling object. In this video, we'll model a falling object with a differential equation and then solve a falling object problem. So for this example, we'll consider a falling object influenced by gravity and air resistance that's proportional to the velocity of the object. So there are two forces acting on the object. The force due to gravity given by the weight, which is going to be equal to m times g, or mass times the acceleration due to gravity, and the force due to air resistance is proportional to the velocity, so it's going to be equal to negative k times v, where k is the constant of proportionality, and it's going to be negative because it's going to be in the opposite direction of the force due to gravity. So the net force, or big F, is going to be equal to m times g minus k times v. Let's take a look at a diagram to get a better feel for what's happening here. If this circle represents our falling object, the force downward, again, is going to be m times g. So in this case, downward will be the positive direction, and therefore the force of the air resistance we're going to label negative k times v, because it's going to be in the opposite direction of the force downward. And this horizontal line here would be the ground. Now let's see how we can come up with our differential equation to model this falling object. Using Newton's second law of motion, we know force is equal to mass times acceleration, where F equals m times a. Well, the first thing we can do is replace acceleration with dv dt, or the change in velocity with respect to time. Next, we now know that our net force, or big F, is equal to mg minus k times v. So here's a differential equation that we can use to model the falling object, but we do want to change the form of this differential equation. So the next step, we're going to add kv to both sides of the equation, which would give us this equation here. And because this is a linear first-order differential equation, we want to write this in standard form, so we'll divide both sides of the equation by m. Notice how this first term would be dv dt. The second term would be k divided by m times v. And then on the right side, the m's would simplify to 1, leaving us with g. So the differential equation that we're going to use to solve our problem is dv dt plus k divided by m times v equals g. It's important to recognize this only works when air resistance is proportional to the velocity. Now let's take a look at our example. A steel ball weighing 1 pound is dropped from 2,500 feet with no velocity. As it falls, air resistance is equal to v divided by 8, or 1/8 times v, in pounds, where v is the velocity of the ball in feet per second. We want to find the limiting velocity and the time it takes for the ball to hit the ground. So to set up our differential equation, we want to find k, m, and g. Let's start with g, which is the acceleration due to gravity. Because in this problem we're dealing with feet, the acceleration due to gravity is going to be 32 feet per second squared, or g equals 32. Again, we're using a positive value here because we're assuming downward is the positive direction. Now we need to find k and v. Let's talk about k, which relates the air resistance to the velocity. Well, we're told that the air resistance is v divided by 8 pounds, or 1/8 times v. So that means k is equal to 1/8. And then for the mass, we need to use the equation W equals m times g. We're told the weight is 1 pound, so W is 1. We don't know the mass, but we know g is equal to 32, so we have 32m. Divide both sides by 32. We have m is equal to 1 over 32 slugs, or just 1 over 32. This gives us all the information we need to write our differential equation. We have dv dt plus, this would be 1/8 over 1 over 32 times v must equal positive 32. Well, 1/8 divided by 1 over 32 is going to be 4, so we have dv dt plus 4v equals 32. Again, this is a linear first-order differential equation, so we're going to solve this using an integrating factor. Let's go ahead and do that on the next slide. Our integrating factor, mu of t, is going to be equal to e raised to the power of the integral of the function being multiplied by v, or in this case, just the constant 4 dt. So the integrating factor here is going to be e to the power of 4t. Now we're going to multiply everything in this equation here by our integrating factor. Now when using an integrating factor to solve this linear first-order differential equation, the left side of this equation, or this side here, is always equal to the derivative of the product of the integrating factor and our function v. So if the left side is equal to this derivative must also be equal to the right side, or 32 e to the 4t. And now we can solve this by integrating both sides of the equation with respect to t. On the left side, the integral and derivative undo each other, so we're left with e to the 4t times v must equal, here we do have to perform a u substitution, where u is going to be equal to 4t, so differential u is equal to 4 dt, dividing both sides by 4. If we write this in terms of u, we'll have an extra factor of 1/4, so we're going to have 32 divided by 4 times e to the 4t plus c. Now we'll solve this equation for v by dividing everything by e to the 4t. So this simplifies to v, or v of t. This simplifies to 1, and 32 divided by 4 is 8. So we have 8 plus, we'll write this as c times e to the negative 4t power. Now we need to find our constant c. To do this, we know that v of 0 is equal to 0. The initial velocity is equal to 0. So that means that 8 plus c times, this would be e to the 0, or 1, must equal 0. Therefore, c is equal to negative 8. So our velocity function is v of t equals 8 minus 8 times e to the negative 4t. So to find our limiting velocity, we need to find the limit of this function as t approaches infinity. Let's go ahead and do that on the next slide. To do this, it might be helpful to rewrite this second term as a fraction. So we would have 8 minus 8 all over e to the power of 4t. In this form, we can see the second term here is going to approach 0 because the denominator is increasing without bound as t approaches infinity. Therefore, this limit is just equal to 8, which means our limiting velocity is equal to 8 feet per second. That's the fastest this object will fall until it hits the ground, due to the air resistance. Now for the next part, we're asked to determine when the object is going to hit the ground. To do that, we want to find the position function. Remember, the velocity function, or v of t, is the derivative of the position function, which means if we integrate the velocity function with respect to t, we will be able to find the position function. So we'll have s of t equals the integral of 8 minus 8 times e raised to the power of negative 4t. Notice again, to integrate the second term, we'd have to perform a u substitution where u is going to be equal to negative 4t. So differential u is going to be negative 4 dt. Divide both sides by negative 4. So when performing the substitution, we'll have an extra factor of negative 1/4. So s of t is going to be equal to 8t minus 8 times negative 1/4 e to the negative 4t plus c. So simplifying here, we'll have s of t equals 8t. It's going to be plus 2 times e to the negative 4t plus c. Now before we find the constant of integration, let's go back to our diagram just for a moment. We know this is 2,500 feet above the ground. We're actually going to let this height here be 0 and let the ground be 2,500 feet. So the object starts here, and then when it hits the ground, it will travel 2,500 feet. So we'll let s of 0 equals 0. So this would give us 8 times 0, that's 0, plus 2 times e to the 0, which is 1, plus c equals 0. So we know c must equal negative 2. So our position function, s of t, is equal to 8t plus 2 times e to the negative 4t minus 2. So to determine how long it's going to take for this object to hit the ground, we're going to set our position function equal to 2,500 and then solve for t. So we want to solve the equation 8t plus 2 times e to the negative 4t minus 2 equals 2,500. Now solving this equation would not be easy. It would actually take trial and error by hand. So what we're going to do is solve this graphically. We'll graph the left side of the equation as, let's say, y1, and we'll graph the right side as, let's say, y2. So if we graph this, the blue graph would be the graph of the left side of the equation, or y1, and the graph of the right side, or the constant, would be the red graph, or y2. So this point of intersection represents our solution. Because we're looking for time, that's going to be the x-coordinate, so it's going to take approximately 312.75 seconds for this object to hit the ground. Okay, we'll go ahead and stop here for this video. I hope you found this helpful.